Welcome back to TechTide Digital Lifestyle, and welcome to Alternator Masterclass Video Series 6. In this lecture we move into one of the most practical and exam-oriented areas of synchronous machines, testing and performance characteristics. On the screen you can see a modern marine alternator surrounded by measuring instruments and characteristic curves, which represent how engineers evaluate generator behavior before placing it into service. Before starting watching this video, subscribe my channel TechTide Digital Lifestyle and don't forget to like this video and comment. Today we will study the open circuit test, short circuit test, calculation of synchronous impedance, and how performance curves help us predict voltage regulation and load response. These tests are routinely used during commissioning, maintenance, and troubleshooting onboard ships and in industrial plants. By the end of this lecture, you should be confident explaining these tests in exams and understanding why they are so important for safe generator operation. Open circuit test, no load test. This slide shows the alternator running at rated speed with its terminals open and a voltmeter connected. This represents the open circuit or no load test. During this test, the generator is driven by its prime mover while no electrical load is connected to the output terminals. The field current is gradually increased, and for each value of excitation, the terminal voltage is recorded. The purpose of this test is to obtain the open circuit characteristic, or OCC curve, which shows how voltage varies with field current. You can see magnetic flux glowing inside the machine, representing increasing excitation. In marine practice, engineers use this test to verify that the generator builds up voltage correctly and that magnetic saturation occurs at expected levels. It also helps in setting AVR limits and excitation control values. For examinations, always remember, open circuit test equals voltage versus field current at rated speed and no load. Short circuit test. Here the alternator is again running at rated speed, but now the output terminals are shorted through heavy conductors and an ammeter, as shown in the graphic. This is the short circuit test. While keeping the shaft speed constant, the field current is slowly increased, and the resulting armature current is measured. The glowing current paths in the stator represent heavy short circuit currents flowing safely through measuring instruments. This test gives us the short circuit characteristic, or SCC curve, which plots armature current versus field current. Safety is extremely important during this test because large currents are involved, especially for marine diesel generators. Engineers perform this test only under controlled conditions. In exams, remember, short circuit test measures current, not voltage, and is essential for calculating synchronous impedance. Synchronous impedance or calculations. This slide introduces the key formula displayed in the hologram, ZS equals VOC, ISC. The arrows connecting open circuit voltage and short circuit current show how data from the two tests are combined. The internal rotor and stator are visible to remind us that synchronous impedance represents the combined effect of armature resistance and synchronous reactance. By taking the open circuit voltage and dividing it by the corresponding short circuit current at the same field excitation, we obtain ZS. This value allows engineers to estimate voltage regulation and predict how the alternator will behave when supplying loads. In marine DG systems operating in parallel, knowing synchronous impedance helps in assessing voltage stability and reactive load sharing. From an examination point of view, you should be able to explain how ZS is obtained and why it is only an approximate method. Performance characteristics overview. On this slide you can see three curves floating beside the alternator, the OCC, SCC, and load characteristic curve. These together describe the overall performance of a synchronous generator. OCC shows how voltage builds up with excitation, SCC shows how current behaves during short circuit, and the load characteristic curve shows how terminal voltage changes when load is applied. The glowing flux patterns inside the machine connect theory with physical behavior. These curves are used by engineers to predict voltage regulation, excitation requirements, and stability during operation. In marine installations, such curves guide commissioning engineers when setting protection limits and AVR parameters. For students and exam candidates, being able to sketch and interpret these curves is extremely important. Open Circuit Characteristic Curve, OCC. Here we zoom in on the OCC curve, a graph of terminal voltage versus field current. At low excitation, the curve is almost straight, meaning voltage rises linearly as field current increases. As excitation becomes stronger, the curve bends and flattens, indicating magnetic saturation in the iron core, which is highlighted in orange on the slide. This saturation region is important because it shows the limit beyond which increasing field current produces only a small voltage increase. Marine engineers refer to this curve when setting AVR control ranges and excitation ceilings. OCC is also used during calculations of synchronous reactance and voltage regulation. In examinations, you should be able to explain why the curve becomes nonlinear and what saturation means physically inside the alternator. Short Circuit Characteristic Curve, SCC. This slide shows the SCC curve, armature current plotted against field current, appearing almost perfectly straight. The linear nature is emphasized by glowing straight line graphics. Under short circuit conditions, the magnetic field in the machine is weak because most of the voltage drops internally, so the core does not saturate significantly. This is why SCC remains linear over a wide range of excitation. Engineers combine SCC with OCC to calculate synchronous impedance and predict voltage drops under load. In marine systems, this information helps in planning safe fault level ratings and protection coordination. For exams, remember, SCC is linear, current-based, and used directly for impedance calculations. Load performance curve. Here the generator is shown supplying different loads, with voltage meters dropping as load increases. The holographic curve displays terminal voltage versus load current, along with icons for lagging and unity power factors. Lagging power factor loads, such as induction motors, cause a greater voltage drop, which is clearly illustrated in the graphic. This curve allows engineers to predict how voltage will behave when large motors start or cargo equipment is energized on board ships. It also guides excitation control and PMS decisions during parallel operation. From an exam perspective, this curve links theory to real operation. You may be asked how voltage changes with load and why AVR must compensate continuously. Practical marine DG applications. Now we move into a realistic ship engine room environment. Multiple generators operate in parallel while a PMS screen supervises voltage, load sharing, and alarms. The glowing arrows between generators represent balanced active and reactive power flow. In real life, alternator tests are used during commissioning to verify performance, after major overhauls, and when abnormal voltage behavior is observed. Engineers rely on OCC, SCC, and load curves to adjust excitation limits, ensure stable parallel operation, and avoid blackouts. Understanding these test results allows ETOs and marine engineers to react quickly to faults, protect equipment, and maintain uninterrupted power supply during critical operations like maneuvering or cargo handling. Summary or exam focus. Let us conclude this lecture. Open circuit tests give us the OCC curve and show how voltage builds with excitation. Short circuit tests produce the SCC curve and allow calculation of synchronous impedance. Combining both helps predict voltage regulation and load performance. These methods are fundamental in marine and industrial alternator testing. For exams, remember the procedures, safety precautions, curve shapes, formulas, and practical applications. Be ready to explain how these tests support commissioning and parallel operation on board ships. In the next video, we will study alternator maintenance and fault analysis, completing the practical side of this masterclass. Keep learning with TechTide Digital Lifestyle, and continue strengthening your engineering expertise. Thank you for watching this episode of the Alternator Masterclass on TechTide Digital Lifestyle. Today we covered essential testing methods like the open circuit test, short circuit test, synchronous impedance and performance curves. Topics that are extremely important for marine engineers, ETOs, industrial professionals and fresh engineering graduates. If this lecture helped you, please like the video, share it with your friends, and drop your questions in the comments below. Don't forget to subscribe to TechTide Digital Lifestyle and turn on notifications so you never miss our next lecture, where we'll explore alternator maintenance and fault diagnosis in detail. Keep learning and stay powered.